In today's class, we are going to start with the next section of chapter 2, which is 2.3, and it talks about different functions. So we will see definition of functions, then domain, codomain. So domain, codomain, image, pre-image, and injection, surjection, and bijection. So those are different types of functions. Then we will see inverse function and little bit about function composition. So this we will not study in this class. So if you look at the definition of functions, then if we say A and B are non-empty sets, so we will see some example later on. But if we say that there is a function which goes from A to B, then there is an assignment for every value in A, and then if we apply that function on that value, then we are going to get values which come from set B. So there is kind of a mapping from set A to set B, and that mapping we call as functions. Now, where it's A and B is coming from, so general, how we discussed before, it is any set A and any set B. So when we take a Cartesian product that we saw in the last class. So when we take Cartesian product, it will have all possible combinations of A and B. So if my A is, let's say AB and B is 1 to 3, then 2 by 3, I have 6 possible combinations, that A1, A2, A3, B1, B2, B3. And when I have to show that in terms of function, it will take some assignments from the Cartesian product. So in other words, we can say that any function f is always a subset of A Cartesian product B, because it will have some mapping where my first element will come from A, second element will come from B, but it might not be all possible combination. In fact, it will never be all possible combinations because of we have one restriction in function that we will see shortly. So let's say from A and B, I'm going to show it graphically. So the set A, it has two elements, A and B. And set B has three elements, 1, 2, 3. 1, 2, 3. Then I might say if I apply one function on set A, I get 2. So we don't know what that function is. If I apply it on B, let's say I get 1. And so my function f will be here. If I apply it on A, I get 2. If I apply it on B, I get 1. So here you will see that it is coming from, those are the two elements from our Cartesian product. So always any function we represent that will come from some elements from Cartesian product. So we can look at it as always being a subset of A Cartesian product B. So we saw Cartesian product, so we will not do it again here. And here with one restriction. So what is that restriction? That B is unique element that is assigned to A. Meaning that if I say every time, if I apply function A, function f on A, every time I'm going to get 2. In other words, it means that if I am having A, the second element will always be 2. I cannot have once I give A, I am getting output as 1. Once I give A, I am getting output as 3. So this kind of, for any one element, every time you apply F, you are getting a unique value. So A cannot have arrows going towards 1, 2, 3, or at a time A cannot have all the 3 values. Out of these 3, only one single value will be there along with A. So that is our restriction. So either we can have A assigned to 1 or A assigned to 2 or A assigned to 3. And that value remains same. So every time we apply A, every time I'm getting the same output. So that is the restriction on function. So it will only have unique output. So function is also sometimes called as input output. So we are giving whatever set A has, those are the inputs, and whatever set B has, those are the outputs of the function. So here we can write that when we apply function on A, we get some B, where B is the unique element. So every time we apply it, we must get the same output. So sometimes functions are also looked at as mappings. And here is one example that this is a student and these are grades. So let's say these are grades from discrete math class. Okay. Now, every time we give the student name, we will get the same grade. So let's say these are final grades. So every time we say for Sandeep, what is the grade? Every time it is going to be B. It cannot be that once we saw it was B, second time it was A. That will never happen. So for the function, so this we can look at it as a function where we have students and their associated grade. Now another thing is we can have grade A to multiple students. So that is fine. So if we have values A, B, both can have value 2. That is fine. As long as we don't want A having or output to output. So that is not possible. So same value can be associated with other elements of set A. So here multiple students can have single grade, but single student cannot have multiple grades. Right. So this is how always a function is implemented. Now, if you look at how this mapping is coming from. So you will see that this mapping will always be a subset of Cartesian product from students multiply a Cartesian product grades. If we take all possible combinations, then out of which there will be one, which is the correct assignment for every student. And there will be 4 such assignments because 4 such students are there. Now, it is possible that from all possible grades, you will see that in this class, out of these 4 students, none of them received grade C, D, or F, and all of them received A or B. So multiple students are getting mapped to a single grade, which is possible. But single student cannot have multiple grades. And it is also possible that some of the values from our codomain are not getting mapped. So if some students of none of the students get grade F, then F will be a value for which we do not have any incoming arrow. So this is Cartesian products, we will not go again. So if we look at more formal definition of function, then it says to be a subset of A Cartesian product B in such a way that it is restricted to no 2 elements have same first element. So in other words, we can say that whenever X is a member of A, and then there exists a Y from set B. So X is coming from domain and Y is coming from codomain. And whenever XY is in the function, then if you say that there is another Y, this is Y1, let's say, and there is another Y2 for which X can be having function with, then X, Y1 and Y2 must be same. So they must be same element. So in other words, it's the same as saying that the output will always be unique, but this is a more formally defined way of saying the same thing. So whenever we are saying X and Y are part of function, then X and Y are coming from separate sets A and B, and X has always a unique value of Y. So now some more definitions about functions. So when we say that we have a function f and it maps A and B, then the set A we always call as a domain set and set B we always call as codomain set, from which the values are getting mapped or outputs are getting mapped. Now, we saw this we also represent as if we apply function on A, we get B. Then B is called as image of A under F. So image of F under image of A under F. And A is called as pre-image of B. So whenever we are applying the function on A, we are getting B. So A is the pre-image of B and B is the image of A. Now, range is all the images under F. In other words, range is all the values from set B which are participating in function. So what is range in this case? So what is the domain in this case? Let's say this is a function under consideration. Students grade. So everything, let's say my domain here is the whole set students. What is the codomain? Grades. Now what is range? What is range in this case? Range A and B, that's correct. So A and B is the range, because range are all the elements of function which come from codomain and which participate in function. Now C, D and F are not participating in function F, so they are not part of range. So in other words, we can always say that range will always be subset of codomain. Okay. Sometimes it is possible that if all students are getting one of these grades, then there will be all arrows going towards these grades and then everything is participating. So we can say in that case, we can say my range is same as codomain. If it is not, then we are going to say the range is a subset of codomain. So most of the times it is subset of codomain. Now here is one. So these are different types of functions. So one we already saw, students and grade. Another function is fx is equal to x plus 1. Now here, if we consider that A holds values, so let's assume that A holds values 1 to 3 and then B has values 1, 2, 3 and 4. And then we are going to show if we apply this function fx is equal to x plus 1, so we are going to add 1 to A and that will give me output. So if I add 1 to 2, it will give me 3, 1 to 3, it will give me 4. And 1 is not participating in the function. So that is one way of representing function by just giving a numerical value. And whatever values we have in A, those values will take the place of X. So we replace X by those values and then we get some outputs which will be part of or which will come from set B. So here, if I have to represent my function F, there are three possible assignments. So we can say F is 1. If I give input 1, I get output 2. If I give input 2, I get output 3. If I get input 3, I get output 4. So you will see that these three numbers again are coming from the Cartesian product set A, Cartesian product B. If I do A Cartesian product B, I'm going to get all the combinations 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, out of which only these three values will satisfy that my function gives me a value 1 greater than the value we entered. So that is one way of representing function. Another way might be we can implement a computer program and then we can say that this is a function. So for example, if we are calculating factorial of a number, we are going to say, I enter value 2 and I get 2 factorial, which is 2 multiplied by 1, which is 2. So inside there will be a function which is calculating the factorial. Or if I enter the input as 3, I get 6 as output. So whenever we have inputs and outputs and those kind of Java programs, we can also look at those as some kind of function. So we in programming language also we call it as a function, but they take different forms. So here are some questions to see if we understood. So some quiz questions. Maybe I should not have solution on the same slide. Okay. So what is the function of A? So if we apply, so this is F. If we apply on A, we get Z. So F of A is Z. What is image of D? Image of D is if we apply function on D, what element we get? Again, we are getting Z here. So that value is also Z. What is domain of this function? This whole set A, that is domain. Codomain is whole set B. What is the image of Y? So we have to say what is for which input we are getting Y as output, and that is B. So the pre-image of Y is B. Now sometimes we also might want to check if we apply that function on whole A, what are the possible outputs we are getting? In other words, what is the range of the function? So if we apply F on whole A, so my whole set A is either A, B, C, and D. And then what? This will be a set of different outputs. So if I apply function on A, I am getting Z. If I apply it on B, I am getting Y. If I apply it on C, I am getting Z. So it is the same element. So I will not write again. If I apply it on D, I am again getting Z. So if I apply function F on set A, then I will have a subset of domain, codomain B, and it will only have two values, Z and Y. Now, what is it? What is it called? The elements which are participating in function. So in other words, YZ is also a range of the function. Now, what are the pre-images of Z? So we have to see all the incoming arrows to Z. So the incoming arrows to Z are A, yes, C, and D. So ACD is pre-image of Z. Is it clear? So in the exercises, you will see that there are more such problems on functions. You can solve those. So some of the problems I have also given in homework 1, which are based on, I think, little more complex problems of function. So now we can also take a set S, which is not exactly set A, but which is a subset from A. So that's, we can say that here my set S, I'm deriving it from A, so it is subset of A, and A has these 4 values. Maybe S only has 3 values, A, B, C. Now, if I say I want to apply this function on S, then what will be my output set? So I am basically going to apply it on A, which gives me Z. I'm going to apply it on B, which gives me Y. And going to apply it on C, which again gives me Z. So that gives me set YZ. So again, order doesn't matter. You can say ZY or YZ, it is the same set. Similarly, now, if I say my subset S is only CD, and I want to find out what is the function if I apply F on these 2 elements, C and D. So in both cases, the function, if we apply it on C, we get Z. If we apply it on D, we also get Z. So here my output will be Z. Okay. So just taking one subset from our domain, we can also apply function only on that subset and then find out what values we can get. So we can, they are also saying this is like a combination of functions and set, because we are taking a set out of our domain. Now there are three types of functions that we are going to see. This is called as injections, not the one we take. It is called as one-to-one function as well. So one-to-one function or injection is a function where every value fa. So whenever we see that on the right hand side, if we apply a on if we apply function f on a, and if we apply it on b, and if we are getting same value, then a and b are same. In other words, for every value we get unique output. So unlike the students and grades example, where we can see that students and grades, multiple students can have same grade, right? In this case, that will not happen. So every element in the domain will have a unique output. So one example of this case might be students and student ID. So if we take student and student ID, then I can see that every student will have a unique ID. So if I have IDs here, I will never have like two students having same ID, like student and grade. That will not be possible in this case. So every input will have a unique output. So that is one example of one-to-one function. Now, let's say there is some possible IDs which are not yet assigned to student. That is also possible. So here on the left hand side, you will see that there might be some possible values in the codomain which are not yet mapped, but from domain, it will always have some output, and that output will be unique output. So whenever we say FA is equal to FB, A is equal to B. We don't have any value which is image of two or more values. That is not possible. Now, second type of function is called as surjection. It is also called as onto function. Another definition of onto function is when every element from the codomain has some pre-image. So that is the one definition here. Another very simple way of looking at is when your range is same as your codomain. So every value on the right hand side is getting mapped. So it has to be output of one of the values which are coming from domain, then we call it as an onto function. So in other words, your range will be exactly same as your codomain. In other words, there are no values on the right hand side which are not participating in function. So everything in the right hand side is participating in function, then we are going to call it as a onto function. So some examples might be now in the same case. If it is students and all possible grades, let's say we have, and every student has gotten at least one of these grades, then we can say that this function is now becomes onto, because whatever is my range, that is my codomain, or everything on the right hand side of function is also part of my function, or everything in the codomain participates in the function. So this is called as onto function. Now, third part, a third definition is a combination of both of these. So a function where it is surjective and injective, or when the function is both one-to-one and onto, then we call it as a bijection. Now in bijection, so a typical bijection will look like this. So every single value will have a unique value on the right hand side. Generally here you can say that the number of elements in A will be same as number of elements in B, because we need to have mapping for each value, and that mapping will be unique. So you can see that here there are 4 values, equal number of value you will also see on B, and for every value we are getting unique output, then that becomes a bijection. Now there are very many properties of bijective functions, those we will see shortly. Now here are some, if you want to prove that this function is one-to-one, if you want to prove that the function is onto, then there are typical ways of doing it. So if you want to show that a particular function is one-to-one, then you show that if you take any value, arbitrary value x, y, and if x is equal to y, then f of x must be equal to f of y. Or the other way around, sorry. If f of x is equal to f of y, then x must be equal to y. If we have to show that it is injective, sorry, it is not injective, then we will find at least one example where we have f of x is equal to f of y, and that is there are 2 values which are getting mapped to A. So if we can show that these 2 values are different, then it means that function is not one-to-one. If we can show that these 2 values are actually same, then it is injective. Similarly, for onto, if it is not onto, then we have to show from codomain, we have to show at least one value which will not participate in the function. So that will show that it is not surjective. So at least one value is such that there is no pre-image for that value, then we can say that it is not onto. And if we find out that all the values in the codomain will be part of function, then that will be that is proof. So depending upon what the proof is, we will show. So here are some examples of functions. So let's solve those examples. So now here we have been given, this is domain. So we have not given set names, but from ABCD to 1 to 3, it means this is the codomain. So in other words, we can say my set A has 4 elements, A, B, C, D. And it is always easy to show function in a graphical manner. So it makes us to view it more. We can say that the pictorial representation is always easy to understand. And then for codomain, we have 3 elements, 1, 2, 3. Now the function f, directly we have given the mappings. So if we apply it on A, we get 3. For B, get 2. C, we get 1. And D, we get 3. So is this function an onto function? Yes. So in onto function, when we have to check what is the range of this function. So what are the elements who have incoming values from the codomain? So 1 has incoming arrow, 2 has, 3 has. So 1, 2, 3 are all participate in the function, and it is equal to, so whenever we see that range is equal to codomain, we are going to say this is a counter function. So when we draw it, it becomes more easy for us to find out the particular type of function we have at hand. So even if they have given the implementation, how after applying function, what we are getting, and then we can see. Now, is this one-to-one function? No. Why not? Yes. So for 3, you can say that there are two values, FA and FD, both are getting mapped to 3. So we want unique assignment. So this is not one. Now, is it a bijection? No. So for bijection, we want it to be both one-to-one and onto. So if any one of those is not satisfied, then obviously it is also not bijection. So when both of these, when a function holds both these properties of being one-to-one and onto, then it is a bijection. If it is not one-to-one, then it is not bijection. If it is not onto, then it is not bijection. Now a second example where the function fx is equal to x squared. Now here we have a huge domain, and the domain is set of integers, two set of integers. So the mapping for this example, our domain is set of integers. So do we remember how do we write set of integers? Which value we used? Z? Yes. So our domain is whole Z. And what is our codomain? Codomain is also all set of integers, two set of integers, so all integer values. Now it doesn't say positive or negative, so we are going to assume that it has both positive and negative integers. And on the left hand side, we will have all positive and negative integers. On the right hand side, we will have all positive and negative integers. And then the function, when we apply it, we get the square on the right hand side. So what do you think? Will it be one-to-one? No? Yes? So if I apply it on 2, I'm going to get 4. If I apply it on 4, I'm going to get 16. So basically all the perfect squares I'm going to get. Okay? Why it is not one-to-one? Yes. So negative 2 will also get mapped to 4. Now will it be onto? Again, no, not all integers are perfect squares. So let's write here and see how it will look like. So maybe since it is all positive and negative integers, here there will be many more integers. Inside for domain, we will have many negative numbers. Then maybe 1, 2, 3, 4, 5, 6, 7, 9, many more. So this -3, since the function is x squared, -3 will get mapped to 9. -2 will get mapped to 4. -1 will get mapped to 1. 0, maybe 1 will get mapped to 1. 2 will get mapped to 4. 3 will get mapped to 9. So we will see that there are two values which will get mapped to a single value, minus and plus. So when we apply this function on -3, we will get 9. When we apply it on 3, we will also get 9. So for every element, we are not getting a unique value. So obviously this is not one-to-one. And the second condition, if we want to check for onto, we have to check if the range is equal to codomain, which is also not the case. So there are many values which are not square, 2, 3, 5, 6, 7, 8. Those values will never participate in the function. Again, if you look at the domain and codomain, if we change it from integers to maybe real numbers, then it will change a little bit. Okay. So depending upon our definitions of domain and codomain, our function, how the mapping happens, it will change. So there are some functions where you will see that if you change the domain and codomain, the function properties might change. Meaning one-to-one might become one-to-one, on-to function might become not on-to, and so on. So it really depends upon what domain and codomain we have. So if, for example, on codomain we only have perfect squares, then in that case our range and codomain will be same, and that will become. So here for the given domain and codomain, it is neither one-to-one nor onto. So now we have another definition. So we saw bijection, and we will see why bijection is important and why do we look at it. So the property of bijection is that since we always have unique mapping, so A gets mapped to Z, B is never going to get mapped to Z. B will have some other output. So since it is a unique assignment, we can do the reverse of it. Meaning that if I change the arrow direction and then if I call that function as f inverse, then I can say that if f inverse of x is C, right? F inverse of y is B. F inverse of z is A, and F inverse of W is D. So we can go exactly the opposite direction and we will get correct values. And that is only possible if the function is onto and a one-to-one. Then only we are going to have these mappings. So let's see the definition of inverse function. So let f be a bijection from A to B. Then inverse of f denoted as f inverse. It is defined as f inverse of y is equal to x if and only if we apply f on x and we get y, then we can say that if we apply f inverse on y, we are going to get x. So here, now this is image, and actually from B, when we say f inverse, we get the pre-image. So by definition, if we inverse B, we get original element A back. So if this is my function f, then from codomain to domain, we call this as function f inverse. So an example here is, I have given very simple example, but if you remember, fx is equal to x plus 1. And in that example, if you say 1, 2, 3, if I apply plus 1, I get these values 2, 3, 4. Now, if I do opposite my f inverse, what will be my f inverse? So how will I get from 2? I will get now want to get 1. From 3, I want to get 2. From 4, I want to get 3. Yes, y minus 1. Right? If I go from left to right, I need to add 1. So if I want to come from right to left, I want to negate 1. So if I do that, now 2 will give me 1, 3 will give me 2, and 4 will give me 3. So that is also one function, one way of looking at inverse. So here, the simplistic way they have shown f inverse. So if it is a function going from A to B, this is a function going from B to A, f inverse. And what they have done is they have just reversed the arrow direction. So if from A to Y, then f inverse goes from Y to A, E to D, W to B, and X to C. So for all my function values, the values now go from, so my codomain now becomes the domain and domain becomes the codomain. So here are some more examples. So we have to find inverse for given examples. So we will see a new word now. If a function can be, if we can find inverse of a function, then that function is called as inversible or invertible. So question, will the inversible function be bijection? Yes, no. So invertible is if you can find inverse. Sometimes it is also called as inversible. And in other words, it is asking us if the function is bijection. Because unless it is bijection, we cannot find inverse. We saw if we need to have a one-to-one alignment, we need to have all the elements in the codomain to be in the range in order to find a proper function. So if it is asked to find it is inversible, in other words, it is asked you to find if the given function is bijection. So again, we have a function, we have set A and B. So set A, ABC, and codomain B, one, two, three. Now, if we apply it on A, we get 2. F of B is 3, and F of C is 1. Now, is it invertible, and what is the inverse? Is it invertible? Is it bijection? So we have to check two things. Is it 1-to-1? Yes, because all elements have unique output. Is it onto? Yes. Yes. My codomain is same as my range. So it is a bijection. So in other words, this is invertible. Now, what is the inverse of this function? So when we have to find inverse, we want to now say B is my domain. So the values of B here, and A is my codomain. And we want to just reverse whatever the arrows are. So it goes from A to 2. So now it will go from 2 to A. B to 3. So 3 to B. C to 1. 1 to C. So this is my invertible or inverse of given function. So if we call this as F, this is my F inverse. So we changed the positions of codomain and domain, and we switch the arrow direction. So that's how you will create invertible function. And again, if you sometimes you might want to check the given domain and codomain are different. So if you look in the homework problems, I think it is for integers, the domain and codomain, or real numbers or rational numbers. So depending upon that codomain and domain, you have to find if the given function is bijection or not. Now here is another example. So z to z. So now it is again set of integers to set of integers. And this is my function. So obviously we cannot now have all integer set, but we will assume that it is again going from some negative numbers to, and it will keep going. Now similarly for p, we will say same set is 1, 0, 1, 2, 3, 4, and it will keep on going. So is f invertible given that the mapping happens from integer to integer? So first we have to check if we apply x plus 1 for -3, what will be my output? -2. For -2, -1. For 0, sorry, -1, 0, 0, 1. And that's how all the mapping will go. Will -3 have mapping? Yes. Yes. So there, because it kind of goes from infinity to infinity, considering every value will have mapping and every value will be mapped. So considering that, what can we say? Is it 1 to 1? Yes, because every value has a unique value. So this is 1 to 1. Is it on to? Yes. Okay. So if we can reach up to some value, then obviously we can also reach to one value less than that. So assuming that it is going to be 1 to 1, it is going to be onto, and that's why we can say that this is invertible or this is bijection. Now, what is its inverse? Again, if we change the arrow directions, that will be my inverse. So from -2, I need to go to -3, from -1, -2, 0 to -1, 1 to 0, and so on. So in other words, again, this is the same function, y minus 1. So that will be the inverse of this function f. So even if the domain and codomain are infinite sets, we can still figure out if the function will be satisfying these properties or not. So we did this. Now there is another example. So we saw this already. Now they're saying if we do it on a real number set, let's say, still if we do we saw that fx is equal to x squared. We saw that not all the right hand side values are having mappings. We saw that. So the perfect squares did not have, only perfect squares will have mapping, proper mapping. So we saw that this function was not on 1 to 1, this function was not on 2. So this is not bijection. So it is not invertible. So we cannot find inverse of this function. So I think we are done with the functions. Any questions you have? So, so far we have covered from chapter 2. So let me go back. So that everything so far we covered was from chapter 2. And we will also have the principle of mutual inclusion, exclusion. I think we already saw some example of that. So I believe 2.1, 2.2, and 2.3. So the mutual inclusion exclusion comes from which section? Do you have access to book? The principle of inclusion exclusion. Do you remember this example where there are, let's say, 20 CS students and 10 math students, And then there are some students who are double major, which we shown by CS intersection M. And let's say those students are 5, then we did 20 and then 10. And the intersecting area is counting 5 twice, once as CS students and once as math student. So we use the principle of inclusion exclusion, which says CS union M will be the cardinality of CS set plus the cardinality of math set minus the intersecting area. So that gave us 20 plus 10 minus 5. So this is principle of inclusion exclusion, and we that will also be part of chapter 2. So I'm not sure which section it appears. Do we have online a copy of textbook? Anyone can say? I think 2.4, maybe 2.5. So all the examples you will see in the homework, those will be based on either one of these topics. So you can start working on the homework, and then you can see me in the office hours if you have any questions. So on e-learning, which are also based on functions as an activity for today. So we can try doing that now. So here this is our activity 3. So if you do not have laptop now, you can just try doing it on solving it on your notebook. And when you go home, you can take picture of it and then upload it as submission. That will also work. So here the given set is a single set, and the function goes from the set to itself. So here, let's say if I have set A, then for my function, we have it between both are same set. So my domain and codomain both is same set, and we have A, B, C, D, same elements, and A, B, C. Now for each of these 3 examples, you can try drawing it as a graphical graph or a graphical structure of a function, and then you can figure out if it is one-to-one. So this first question asks about if all these 3 assignments of f are one-to-one. Then similar second question, again same set and same set as domain and same set as codomain. Similarly, we saw last time the set of integers to set of integers. So here also similarly the domain and codomain are same, and the mapping is given. Now for each case you can show the mapping and then check if this particular mapping gives rise to onto function or not. And each of these you have to check if this is onto or not, onto or not. Then for third, it is you can say it is not a fixed answer question, so kind of open-ended, where you have the domain as n, codomain as n. So anyone remembers what is n? Natural number set. And it starts from 0. So it was 0, 1, 2, up to so. So all the values from domain are coming from natural number. So 0, 1, 2. Similarly, for codomain, it is 0, 1, 2. And here you are asked to find the function and satisfying certain properties. So again, every one of you can come up with the different answers. As long as it satisfies those properties, it will be considered as a correct submission. So a function which is one-to-one but not onto. a function that is onto but not one-to-one, a function which is both onto and one-to-one, and neither one-to-one nor onto. So we have to come up with functions which satisfy this property. So again, I can expect different functions.